Welcome. In this lecture we're going to talk about rotational kinematics, which is really just the movement of things going in a circle. Up to this point in the semester we've really just looked at linear motion. So we have maybe a box right here and it's moving to the right with some velocity. It might have some acceleration, maybe going back that way to the left. And we also talked about the box's position. If this is x initial and the box moves to the right at x final before it stops, then we know that we have some displacement of the box. In the rotational world, things work very similarly. I want you to envision a bicycle wheel, and let's say that this bicycle wheel is spinning, and it's spinning counterclockwise. Well, if we pick a point on the bicycle wheel right here, and we look at the rotation of that point on the bike wheel from one place to another, then we can see that it's rotated through some angle. So the position, the equivalent of our x in linear, is given by theta. So the original position we could call theta naught. The final position of the bike wheel we could call theta final. So theta then is equivalent in the rotational world to x in the linear world. It is the angular position. So theta equals angular position. And just like you've learned in math class, either calculus or trig pre-calc, we are normally measuring our angles in radians. So that is the standard unit for angles, for the angular position. And in fact, the radian is a unitless quantity, because when you get down to it, 1 radian is the distance along the rim that is equivalent to a radius. So that's r, and this is r as well, so you end up doing r over r. And the unit for r here would be meters. Meters divided by meters is 1. It's unitless. So we call it a radian, but technically it is a unitless quantity. All right, now this moving from theta naught to theta final didn't just happen instantaneously. It happened over some amount of time. So it had a velocity. It had an angular velocity. And in the rotational world, our variable for angular velocity is called omega. So omega then is the angular velocity. And I'm going to be very specific here because just like in the linear world where x and v are vectors, my theta and my angular velocity, omega, are vectors as well. The unit here is going to be radians per second, angular velocity over time. And technically, radians, again, is a unitless quantity, so we could also write this as 1 over seconds, which you might remember is also a hertz, Hz. So all of those are equivalent, radians per second, 1 over second, or hertz, frequency. And then finally, let's say this wheel is slowing down. It starts out at theta naught and it ends up at theta final, slows down and comes to rest, which means that we also have an acceleration. The wheel is slowing down. Just like in the linear world, if the wheel is slowing down, if the object is slowing down, angular velocity and acceleration have to be in the opposite direction. So if angular velocity is going counterclockwise and it's slowing down, acceleration must be in the opposite direction, which is clockwise. So we define here alpha, which is the Greek letter alpha, as the angular acceleration. And the unit here is going to be radians per second squared, or technically, mathematically, 1 over seconds squared. Those are our variables for at least describing position in the rotational world. So being specific here, in the linear world, our equivalents are x, that's equivalent to theta, and v, that's equivalent to omega, and a, that's equivalent to alpha. All right, once we were able to define our quantities for being able to describe motion, then we're able to go further and look at equations to relate one to the other. All right, working out the equations for rotational kinematics are not difficult because they look identical to the equations that are in the linear kinematics, just different variables. So linear world and rotational world. And again, I want you to envision a bike wheel when you're looking at the rotational world. So the very first equation we had in the linear world was for displacement, delta x. That was x final minus x initial. So same thing over here, except it's change in theta. This is called the angular displacement. We have theta final minus theta initial. And we should mention here, remember in the linear world that to the right was positive and to the left was negative? We have the same sort of thing going on in the rotational world. Unfortunately, it works the exact same as it does on the unit circle in math. If we go counterclockwise, that's defined as positive. And if we go clockwise, that's defined as negative. All right, so if we are at 0 radians on the unit circle and we move to 90 degrees, then we've gone pi over 2 radians. We've got an angle measure of positive pi over 2. All right, so those sign conventions are the same as they are in math. Next equation that we had average velocity over here. Average velocity was equal to the change in the displacement, or the change in position, the displacement divided by the time. Same thing over here. The average angular velocity is going to be the angular displacement divided by the time that it took. Now, beyond that, if the acceleration is constant, actually, before we even do that, we had one more equation for acceleration, didn't we? And that was the average acceleration was equal to the change in omega divided by the time. Same thing over here. The average angular acceleration, I just used omega over here. Let's change that. That's going to be change in the velocity divided by time. Average acceleration over here is going to be, there's the omega, change in omega divided by time. Now, based on this equation that we just wrote down, if A is constant, then we got all of our kinematic equations. All right, so the first one comes from rearranging this equation that we just wrote down. And it was the V final equals V naught plus A times T. Writing that over here in the rotational world, we have if alpha is constant, then we have omega final equals omega naught plus alpha times time. The other ones that we had here were x final equals x naught plus v naught t plus 1/2 at squared. Replacing the variables, we have theta final equals theta naught plus omega naught t plus 1/2 alpha t squared. And the final one, usually the most useful one, we used a lot, v final squared equals v naught squared plus 2 times a times delta x. And translating that, we have omega final squared equals omega naught squared plus 2 alpha delta theta. Okay, so the equations are going to work the same. Our variables are different, our units are a little bit different, and let's remember our sign conventions. Going back to the first page, if we're using those as our sign conventions, in the bike wheel that we had initially, omega here is going counterclockwise, so that would be a positive. Alpha here was going clockwise, that would be a negative acceleration. Next we have what I like to call the wormhole equations, and these relate the linear world to the rotational world, because the linear world is a universe all its own, the rotational universe is all its own, and how do you get from one universe to another? You go through a wormhole. So these wormhole equations will show us how the linear world and the angular world or the rotational world are related. So again, picture a bike wheel, and picture a point on the end of the bike wheel. Okay, so let's say we start out at theta naught is equal to 0 radians, and we come up here and we're at some displacement, delta theta. Theta final minus theta initial. So if we look at the path that this little object travels along the rim of this bike wheel, then we have a delta x here. And we also have a radius of this wheel from the center out to the rim. So how is theta related to delta x? Well, notice that delta x is the arc length. And how is theta related to the arc length? It's the arc length, delta x, is equal to r times delta theta. So there is our first wormhole equation. If we want to relate the linear distance traveled, then we just have to do r times the angular displacement. And this is where that unit for angular displacement, for angular position comes into play, where the radian is unitless, because our unit here for r is in meters. The unit for theta is radians. Go back. Is radians, which is technically unitless. So what is then the unit for delta x going to be? Meters, which it has to be. All right, so delta x displacement, linear displacement, is equal to the radius times the angular displacement. That's the first wormhole equation. So think about a bike tire rolling along the ground without slipping. If it travels through a certain angular displacement, and we know the radius of the bike wheel, we can find the distance the bike wheel traveled. This is how bike speedometers work. This is how car speedometers work. If we change the radius of our wheel, but we don't change how that radius is computed in our calculator, in our bike computer, on our speedometer in our car, we're going to get the wrong linear speed. Okay? So first wormhole equation here. Second wormhole equation, this displacement delta x doesn't just happen instantaneously, it happens over time. So if we divide both sides of that equation there by time, we have delta x over t is equal to r times delta theta over t. And delta x over t is omega, and theta, no, wrong. I keep getting it backwards. Delta x over t is the linear velocity, and delta theta over t is the angular velocity. So there's our second wormhole equation. The linear velocity is omega times the radius. And again, the units work out here. The units for r are meters. The units for omega are radians over seconds, but radians is unitless. We end up with meters over seconds for our linear velocity. The units work again. And you can probably guess, if we divide by time again, velocity divided by time is going to give us a, the acceleration. So our third wormhole equation is the acceleration, the linear acceleration, is equal to r times alpha. And that's the third wormhole equation. So we can relate the linear world, linear displacements, linear velocities, linear accelerations, to the angular world through these wormhole equations. So next, don't forget about centripetal acceleration. We've got stuff going in a circle. So we have a centripetal acceleration that is pointed straight in towards the center of the circle for the object. So the wormhole equation will give us the linear acceleration, which is pointing this direction for this object. So a sub L, the linear acceleration. The centripetal acceleration always points in towards the center of rotation. And we remember that the centripetal acceleration, a sub c, is given as the tangential velocity squared divided by r, v squared over r. Well, using that wormhole equation that we just had, v is equal to r omega. We square that sucker, dividing by r still, we have r squared, omega squared over r. So one of the r's cancel, and we end up with r omega squared. So we can calculate the centripetal acceleration of any point, a sub c, is equal to r times omega squared. All right, and that's another kind of wormhole equation, but that's how we calculate the centripetal acceleration if we know omega. So theoretically, we also, or realistically, we can have an object that has an angular acceleration. So at that point, not only would it have a centripetal acceleration, which is the red arrow here, it would also have a linear acceleration here. So if we wanted to find the total acceleration of that point, moving these vectors over, we have the centripetal acceleration here. We add these vectors tip to tail. If this is the linear acceleration here, then our resultant would be the total acceleration a. And it would have a direction that's not pointed in towards the center. It's not pointing tangentially. It's pointing off at some angle. And we could find the total acceleration. All right, so keep that in mind. Linear acceleration is going to be tangent to the circle. Centripetal acceleration is pointing in towards the center. And the total acceleration is the vector sum of those two. Let's take a look at an example that's going to show us some of the interesting phenomena that happen with the rotational world. We've got a record player, two ladybugs on it. One's at the edge and one's halfway to the edge. The record player has a max speed of 33 RPMs, and let's compare the velocities and accelerations for the two bugs. Okay, so first, let's take a look at their angular velocities when the record player gets all the way up to 33 RPMs. So let's call this inner one Ladybug 1, and the outer one is Ladybug number 2. All right, so at 33 RPMs, first off, it's disguised, but that's actually an angular velocity. Omega equals 33 revolutions per minute. And we've dealt with these conversions before. The standard unit for omega is not revolutions per minute, it's radians per second. So we need to convert into radians per second. So first, let's convert revolutions to radian. 1 revolution is all the way around the circle once. That's 2 pi radians. And 1 minute is 60 seconds. So that is going to convert revolutions per minute into radians per second. And you know what? I know record players spin at 33 1/3 RPMs, but for ease of math, let's just go ahead and change this to 30 RPMs and just make the math a whole lot easier. So we're going to have, let's see, 30 divided by 60 is going to be 1/2, and we are going to divide the 2 pi by 2, and we're going to end up with pi radians per second. That's pretty easy, isn't it? Okay, so we have an angular velocity of pi radians per second. We got to think, who has that angular velocity? Is it Ladybug 1 or Ladybug number 2? And when we think about it, Ladybug 1 goes once around the circle in the same amount of time that Ladybug 2 goes once around the circle. It's true that Ladybug 2 travels a greater distance, but that's going to play into the linear velocity, not into the angular velocity. So both Ladybugs, omega 1 is equal to pi radians per second, and Ladybug number 2 has an omega of pi radians per second. So we see that their angular velocities don't depend on where they are on the record player. Now let's look at their linear velocities. V1 is going to equal r times omega 1. So since Ladybug number 1 is half of r, we're going to have 1/2 r. This would be r1 times omega 1. So Ladybug 1 is at half the radius times its angular velocity. So we have pi r over 2 for the velocity of Ladybug 1, and for the velocity of 2, it's simply r2 times omega 2, which is going to be r times pi. And this is in meters per second. All right, so we've got Ladybug number 1 has half of the velocity of Ladybug number 2 if we look at the linear velocity. That totally makes sense because Ladybug number 1 is traveling less distance than Ladybug number 2. So Ladybug number 2 better have a larger linear velocity than Ladybug number 1. So in the rotational world, we see that the angular velocities don't depend on the radius. The angular velocity is the same no matter where you are in reference to the center of the circle. But the linear velocities change. The further out you are, the faster linearly you are going. Let's see if that holds true for accelerations. So first, we know that if this record player starts at an angular velocity of 0, it's going to go up to 30 RPMs in some amount of time. Let's just call it time t. Okay? So for alpha 1, we know that the alpha is equal to omega divided by the time. So alpha 1 is going to be omega 1 over time, and omega 1 was just pi. So we have pi divided by t, and this is going to be radians per second squared. And alpha 2 we see is going to be the same. Since their omegas are the same, that means that their accelerations are also going to be the same, because it takes the same amount of time to spin up from 0 to 30 RPMs. And so we see the same trend here. The alpha, the angular accelerations, are the same for both ladybugs. Are the linear accelerations the same? Again, A is equal to r times alpha. My students last year memorized it by acceleration equals ralpha. I don't know if it helps you or not, but A1 then would be r times alpha 1. That would be r1 times alpha 1. So r1, first ladybug, is r over 2 times alpha 1, which is pi over t. So we have half of r pi t. And that's going to be in radians per second squared. And when we look at alpha 2, that's going to be omega 2, whoops, sorry, that would be R2 times alpha 2. So R2 is R, the full radius, and alpha 2 is the same, pi over t. And we see the same trend that we saw with the velocity. The linear acceleration for the outer ladybug is twice as big as the linear acceleration for the inner ladybug. That's not the only acceleration we can look at, because both of these ladybugs have a centripetal acceleration as well. You can think about it as this record player speeds up, there's a certain amount of friction between the ladybug's feet and the record player. Who's going to spin off the record player first? It's going to be the ladybug that has the greater centripetal acceleration, because they need the greater centripetal force to keep them going in a circle. So the centripetal acceleration of both bugs, if we look at AC1, remember that would be R1 times omega 1 squared. And R1 was R over 2, and omega 1 was at maximum speed, 30 RPMs, was pi squared. And this is going to be in meters per second squared, centripetal acceleration. The centripetal acceleration of ladybug number 2 is going to be R2 times omega 2 squared. And the radius for the second ladybug is R, and his omega was the same, pi squared, meters per second squared. So again, we see that the centripetal acceleration here is twice as big for the outer ladybug as it is for the inner ladybug. So the outer ladybug has to hold on tighter, and it is going to fall off first as the record player spins up, depending on our force of friction. All right, so we could easily plug in numbers for these and figure stuff out. So you are going to work a problem set when you get to class, and I will see you later.